Hello, good morning, everyone. I'm usually starting 1 or 2 minutes late to give everyone the chance to join. I think we already got most participants available, so I think I'll start now. My name is Paul Spanbock. I'm Sales Director at Lumitronics, and I'm very happy to have you all here to our webinar today. Rethink LED module design. We will focus very much on the thermal path in LED module design, enabling a very interesting 3D formable electronics. And my colleague, our engineering director, Volker Kokula, will show most of the slides. But firstly, let me go a little bit into technical aspects of this webinar. We will have a recording of this webinar, which you will be able to download afterwards. So if you want to share the webinar, you can share it also later on. We will offer the slides as a download, which you can check and share also. And we will have a Q&A session after my colleague Volker finished, and you'll have the opportunity during the webinar in the area of Q&A or F&A if you have the German Teams version, to put your questions, and we will answer all the questions after Volker finished the slides. So Lumitronics is a LED lighting specialist. We're working to develop and produce light sources since 20 years in Hechingen in the south of Germany. We are only doing this, nothing else, and we have specialized very much on the production of flexible LED modules based on flexible PCB material, which we can use in length of up to 100 meters continuous PCB. So basically, you can see it in the picture. It's one PCB, which can be in the length of up to 100 meters and in the width of up to half a meter. Now, with flexible PCBs, very many customers have concerns if the flexible PCB will enable very good thermal management. And we can confirm, due to vast experience in this area, that we have found solutions to enable flexible PCBs to be used also in very challenging thermal applications. And we especially have been using flexible PCBs for UV and UVC applications, in which you might know that we still have a very low efficiency on the LED side, which generates up to 95% of heat from the electricity, from the power input to the LED. So very good thermal management is absolutely mandatory, even though in areas of white lighting we have very good efficacy, and thermal path is not that relevant in many applications anymore. But we have developed our product technology to enable a very good thermal path in flexible PCBs, and I would like to hand over to Volker to give you more details about our findings and to give you a little bit of background and explanation on the technology.
Yeah, thank you very much, Paul, for this introduction. My name is Volker Kokula. I'm the head of development at Lumitronics, and I'm working in this function for more than 15 years now. And it is a pleasure for me to discuss with you how to rethink LED module design. Before we can rethink the module design, we of course need to make sure we understand why we even think about the thermal design of LED modules. And therefore we'll go into a bit of background information before we show how we can increase the performance and use flexible PCBs for very demanding thermal applications. We know that LEDs generate heat at the LED junction. And of course, after a certain amount of exposure to heat or very high temperature, every component of a PCB will be damaged. But even significantly before LED or other components are lost due to thermal overheating, we already see a decrease of the LED performance caused by inefficient heat transfer, and we also see an impact on the lifetime of a product if the heat is not managed correctly. So therefore, let's together look at the thermal path of how the heat is normally transported from the heat source, the LED in this case, to the surroundings. Heat is generated at the LED junction and then is first conducted through the LED itself and through the solder to the PCB. In the PCB itself, heat is conducted through the PCB material itself from the top to the heatsink, and also the heat is radiated away from the PCB and the heatsink and also convected away. So we see there are three modes of heat transfer. First is conduction. Conduction is what we normally think of heat transfer. It is the transport of heat from one particle to another particle. The next is convection. Here, the heat is not transported from one particle to another particle, but the particle containing the heat energy itself is moved away, moved through fluids or through gases. And the last mode of heat transport is radiation. In radiation, you don't need a medium, but the heat energy is radiated away through electromagnetic waves. We will now look at those three modes of heat transport in a bit more detail. The first one we want to look at is convection. Convection is normally used, of course, from the PCB itself, but also aided by using some kind of heatsink, which is then used to exchange with a medium surrounding, like the air and or also liquids. What you have to keep in mind here is that the design of the heatsink can have huge impact on the efficacy of the heat transfer. Not only the designs, like how the fins are made up, but also the orientation of the heatsink. So you need to understand the application your light source will be used in order to make most of the heatsink you are buying, you're adding to your product. The next mode of heat transfer is radiation. As said before, radiation is the heat transfer via electromagnetic waves. Here we know that every material is radiating heat, and the most efficient way of radiating is from the surface, and therefore in our PCB design and our LED module design, we need to make sure that the heat is spread evenly on the surface of the PCB so that the heat can then effectively get radiated away. For mid-power LED modules, we need to keep in mind that this is one of the most important methods of thermal management. And last, we will look into conduction. Here, the heat is transferred from the inside the PCB to from the inside of the LED to the outside of the LED, and then from the solder to the PCB to the heatsink. We need to keep in mind that the efficacy of the heat transport through conduction depends on the thermal conductivity of a material and its thickness. So not only the conductivity, which can be very high for certain materials, but also the combination with its thickness is important. We have added a table where we can see some kind of comparison. For example, copper and silver are very good, and also aluminium is quite high compared to other materials like FF4 and PI. And we will, in this presentation, focus on how we can use a material like flexible PCBs like PI for very good and comparable to EMS material PCBs if we do a very good design of the module. Next, let's look at two more important characteristics of heat transfer. One is the thermal capacity, which is for continuously driven LED modules not that important because as soon as we have reached a steady state, the capacitance of the heatsink is not that important. But for example, if you have an application where you need very high flashes of light for a short amount of time, so that then the heatsink has the time to radiate away the heat which has been kept inside the heatsink, there you have to look into this. For a steady driven application like an LED module in general lighting or an LED module in reactors, the heat resistance is more important for the heat conductivity. The heat resistance describes the increase of temperature per energy of input. And we have to make sure that we have no choke points where the heat is not transported very efficiently inside our LED module. And we can verify the thermal resistance, and especially for hotspots, very effectively using thermal imaging and verify it with temperature probes. Now that we have looked at the basics of heat transfer, let's look at an example. In this example, we have a heat source, which is the chip inside an LED, which is generating 0.5 watts of heat. From the chip itself, the heat first has to be conducted through the LED to the solder interface. In this example, the thermal resistance is 14 kelvins per watts, and since we have 0.5 watt of input power, the temperature increase will be 7 Kelvin. Next would be the solder itself, like the legs of the PCB, of the LED to the PCB is connected through solder. Since this is only very tiny, also the thermal resistance is tiny. Here it would be 0.5 Kelvin. Then we have the thermal resistance of a PCB, like from the top of a PCB, we interface to the solder to the bottom of a PCB. In this example, we have 25 kelvins. From the bottom of the PCB, then we use a thermal interface material to connect it to a heatsink, and then finally the thermal resistance of the heatsink itself to the surrounding. And if we then calculate this backwards and start at an ambient temperature of 25 Celsius and add all those increased thermal resistances, which are 30 Kelvin, we come back to a junction temperature of 65 Celsius. And now even for the ambient temperature is 25 Celsius. If we only look at heat conduction, in this example, the junction temperature would be 65 Celsius. and all of the other calculations like lifetime and optical performance have to be done at 65 Celsius. And what we want to show you now is that if we focus on the thermal resistance of the PCB and also on we stack as a whole together with the TMI, that we can achieve good thermal results if we use an optimized flexible PCB stack. For this, we have done tests. We used a high power LED at light source as heat source. This LED was then soldered to PCB layer stack, where the layer stack is the variable we want to change throughout our testing. For all those different tests devices, we have not used cover layer or lacquer in order to make sure we have comparable results. We will go into the different kinds of devices we have tested, the test matrix in a bit. Next, PCB itself is thermally bounded to a standardized heatsink. In this case, it's a block of aluminium of a fixed size. And what we want to do is compare the temperature of the PCB top to the temperature of the heatsink in order to look at the efficacy of the heat transport. The test matrix we have come up with will compare different kinds of base materials. So we will look at FR4, which is more of a default for many PCB applications. We'll use as at aluminium PCBs, and we will also look at flexible PCBs using PI as base material. Moreover, this matrix is expanded by one layer design versus two layer designs where we will use a top copper and a bottom copper, each with 35 microns of copper, and they are connected to each other with thermal vias, like you can see on the bottom row. Also, we will compare different dielectric thermal conductivities for aluminum, and we will look at different thermal interfacing. In this presentation, we will focus on the difference between screwing the device under test onto the heatsink without a TMI and using glue bonding. For each test, we have driven the device under test with a controlled current in a thermally controlled environment. We have observed the temperature rise for the top PCB, like the hotspot temperature, and to the temperature of the heatsink. And we have performed all of those tests until thermal equilibrium is reached. After doing all of those tests, we have derived at a test matrix. In this test matrix, as I told you before, we will compare the temperature difference between the hotspot temperature on the top and the temperature of the heatsink itself. Since this is a proxy for the thermal performance of heat transfer of the used layer stack. The smaller the temperature difference is between the top of a PCB, the hotspot temperature, and the heatsink, the more efficient the heat transfer through the layer stack itself is. Let's now look into those results in detail. At first, we'll focus on the FR4 results. Even without going to any special PCBs like aluminium or flexible PCBs, you can see that it's possible to optimize the thermal performance of an FR4 base material. There, of course, is a difference between using only screws and gluing it to a heatsink, but also you can do optimization using an optimized layer stack. So by using a two-layer PCB and using thermal vias, we can significantly increase the thermal efficiency. If we now focus on the aluminium PCBs, we see a similar result. When optimizing the layer stack at all, we can increase the efficacy of the heat transfer, which this can be done by using an aluminium PCB with a dielectricum, which has a better thermal conductivity, but this can also be optimized by using different bonding technology. And finally, if we look at the PI results, we can see that using an optimized layer stack with flexible PCBs, we always come around, we come around to the thermal efficacy, which can traditionally be reached with IMS material. Let's now look into all of those in detail. We want to look at comparing the different mounting options of rigid boards using screws without a TMI and using thermal epoxy. You might ask why we only compared screwing without a TMI to screwing to gluing and not using screws with a TMI like a plastic, like a glue. The reason is that for a small PCB where you have a very controlled adhesion and the mounting pressure for screwing itself is quite efficient. And you can see that we have a consistent increase in the thermal performance when using the thermal epoxy. This doesn't mean that thermal epoxying is the best solution for every application. There are applications where screwing without a TMI is perfectly fine, but we can see that using an optimized TMI will increase the thermal performance. For the next slides, we therefore will only look at the thermally epoxied solutions. Next, we look at what can be done when using an optimized layout. In this case, we are comparing the FF4 PCBs, which are one layer, with the FF4, which are two layer, and also with PI. And we can see for the same kind of mounting method used, in this case screwing or gluing, we always see an increase in heat transfer efficacy. And this is not obvious, especially not for the flexible PCB, since the flexible PCB is very thin, and as we have covered before, the efficacy of the heat transfer is not just the base material conductivity, but also its thickness. And in this case, when going from one layer PI to two layer PI, we are heading in a whole new layer of copper on the bottom, so the PCB itself will be thicker in total. But still, when using an optimized PCB layout with many thermal vias in order to aid the heat transfer from the top through the PCB to the bottom layer and from there to the heatsink, we can see those increases. And lastly, we gist of this presentation is that we will look at rigid versus flex LED module design. I've clustered the results into what I call basic and advanced layouts. The main difference is the price here, but we see for all of those that the PI will reach a comparable thermal efficacy than an already optimized PCB using traditional methods like aluminium. And this does not mean that PI will deliver the absolute best thermal performance for all possible scenarios. But what this does mean is that PI can be used for formally challenging applications while also having the advantages of a flexible PCB, which can be used for 3D formal applications and be used for very demanding applications like bioreactor design. And now, after I've presented you all those findings, let's think about why this is the case. Why we see that flexible PCBs have a comparable can reach a comparable performance to aluminum PCBs. We want to look at one of the slides we had at the start of this presentation, where I told you the heat transfer, which goes from the chip itself and through the LED to the PCB and through the PCB to the luminaire. And what we can see is that the aluminium of an aluminum PCB has a very high conductivity, but the PCB itself has a significantly lower conductivity compared to only aluminum, and this is because of the dielectricum used between the copper layer and the aluminum layer. And when we compare this to a flexible PCB, it looks almost the same, but without the aluminum spreader in between. We also have the chip creating the heat, which is then conducted to the PCB, and from the PCB it's conducted through an isolator to the housing. And now that we have looked at the PCB design and how to rethink LED module design, I would like to hand over back to Paul for final words in this presentation.
Thank you very much, Volker, for the very detailed presentation. I think it might have been gotten very much more clear why flexible PCBs with a very, very little thickness of the PCB base material offer a very good option to create PCB design with a very low thermal resistance. I think these options enable us in the future to offer designs, LED module designs, for many applications which have very demanding challenges to create light in 3D shapes. We see such applications especially in medical lighting, but also in optical visioning systems and in applications which are very close to the human body. In many of these applications, we need a lot of light, we create a lot of heat, maybe also because LEDs might not yet be as efficient, especially in the area of UV and UVC technology. And it is greatly beneficial to be able to create a 3D bandable PCB, which can still sustain a very good thermal management. So I would like to get to the point where we can offer you to answer questions in the Q&A. You can also put your questions in the chat, but the Q&A is actually the place where it should, which is supposed to be used for that. But yeah, in the end, it really doesn't matter. So the first question we got from Thomas Westerhoff is, how thick is your insulation layer at the flex PCB? Thank you, Thomas. I will hand over to Volker.
Yeah, this is an excellent question. In this case, the base material was 50 micros, which is comparable to what is used in aluminum PCBs, where the dielectricum is usually between 50 and 150 microns big.
With flexible polyimide base material, we can also go down to a thickness of 25 microns very easily. That is available on the market, and we can even go further down, but it's also a question of electric isolation at some point, because the lower the thickness, the lower the electrical isolation. One aspect we would like to highlight is also that not only the PI layer or the dielectricum layer at the aluminum PCB is very important to consider when choosing the stack up of your PCB design, but it is also very important to consider that in many PCBs, most of the PCBs actually, glue is used to laminate the layers together, and this glue can have significant thermal resistance. And we have experienced cases in which customers used very good thermal conductive layers in aluminum PCBs, like 8 watt per meter Kelvin, but the PCB was actually not performing as good as other aluminum PCBs with only 3 watt per meter Kelvin. So much less good thermal conductivity in the dielectricum, because it was using worse glue. So it was using glue layers which added thermal conductivity, which was not transparently visible in the datasheet at first glance. So I'll give you maybe 2-3 additional minutes to consider if you have any added questions, because right now we don't have any more questions in the Q&A area or in the chat. But I'll just give you a minute or two. Maybe someone's coming up with something interesting. In the meanwhile, let me give you the information that we will have the presentation as a download afterwards. You will have the opportunity to also get the recording of this webinar as a download, and naturally you can connect with us on the phone, via email, or have a Teams meeting. We have one more question from Christoph Seibert. I'll translate to English. Have the tests been conducted with screws without thermal interface material?
Yes, test results presented here were done for screwing without thermal interface material. The reason being is that since the devices under tests are very small, in this case we can have a very consistent and good contact by screwing. And we have also performed cases where we used thermal conductivity foil as together with screwing here, and benefits are not as good as you might imagine in this case, since the device under test was very small. We will have bigger difference between screwing without TMI and screwing with TMI if the LED module is larger and you don't have this kind of good contact and pressure evenness.
Thank you very much, Christoph Seibert. Let me see if we maybe have one more question. one person, SB, is holding up the hand. I can try to actually activate your microphone. We are not usually doing that, but let me see. You can try to activate your microphone now. I have allowed it. We have one more question from Dr. Wolfgang Käfer. Do you also have experience with complete plastic systems, meaning placing the PCB FPC on a plastic base using plastic housing? Are you also working with thermal conductive plastics?
Especially for, yeah, Paul,
Volker.
go ahead.
Volker, sorry.
Yeah, sure. Especially for mid-power modules, using a housing made of plastics is a state-of-the-art. Using aluminium housings or even aluminium PCBs is more done for high-power applications. So we plastic housing there is more for mechanical stability and less for the heat management of a PCB. Since for mid-power designs, most of the heat is actually radiated away and not conducted away.
We have conducted a lot of experiments with thermally conductive plastics, but honestly speaking, we are not a plastic manufacturer, so we are not doing plastic molding, plastic injection, and we are always cooperating with partners. From our experience with heat conductive plastics, you're able to improve the heat design and even achieve pretty nice designs, but it's not viable for very demanding technology. So if we are talking about very demanding, we're sometimes talking about heat generation in the area of hundreds of watts, maybe even kilowatts of heat. So in these areas, plastic is usually not working very well anymore. But for smaller products with small amounts of heat generation in the area of maybe a few watts only, it might be a very viable option. Thank you very much. And I think we don't have more questions at the moment. We're looking forward to meet you in the future. You can contact us by email. You can also contact us by phone and directly book a meeting in Teams with us to dive into detail with your technical requirements, with your thermal problems, and see if we can find a good option to solve it. Thank you very much and have a good day. Have a nice week. Goodbye.